So, now this then pushes us into third order nonlinear effects, which we are going to examine now in a nutshell again. We are not going to elaborate this spectacularly. So, the point that we wish to make with regard to third order nonlinear effects is to consider in the case of chi3 effects or chi3 media. Recall earlier we had the polarization vector to be written out as chi1 ij ej plus chi2 ijk ejk plus chi3 ijkl ej ek el, right. So, we examine the effects of chi1 and chi2 on these media. Now, we look at the effects of chi3 on these media, and here we look for, in the case where a beam E is equal to E naught minus I omega t oscillates at a frequency omega, and this such a beam is propagating through a medium with appreciable chi3. Now, as a consequence of the kind of interactions we considered earlier, if we had a beam propagating in a medium and examined its the quadratic nonlinear effects due to chi2, we got terms like we got twice omega, that is second harmonic generation, and in this case with just a single beam propagating at frequency omega, we got twice the frequency being generated. We also got a zero frequency generation term, which is omega minus omega happening, right. Likewise, in a chi3 medium, we need to consider third order effects. So, in the scenario where a single beam is propagating through a medium, there are no other partner beams which are independent. Third order effects will of course lead likewise to 3 omega generation, that is third harmonic being generated. 3 omega is generated as omega plus omega plus omega. Okay. This would be as a consequence of E cubed kind of product terms. Okay. Whereas, we can also have a scenario where we have the following: omega plus omega minus omega being generated, which is equal to omega. Okay. So, this is not third harmonic generation. This essentially arises out of terms where the triplet contains an E star, E star E, or we can consider other scenarios E star. I should use these indices to differentiate them, these three fields, right. So, all these product terms will give rise to the term which is oscillating at omega, but its coefficient is chi3 and not chi1. Okay. So, now if I consider the polarization oscillating at frequency omega, I am left with two terms in this expression which are of the type like this. Now, furthermore, if the medium is say isotropic, then direction does not matter. It does not matter in which direction the beams are polarized, J, K or L. J, K, L can of course take the 3 eigen directions x, y, z. These are the combinations available. In isotropic media, I can of course therefore write P omega to simply be epsilon naught chi 1 E plus epsilon naught chi 3 E multiplied with the E star term becomes absolute value square of E, and this multiplies E. Therefore, the polarization oscillating at omega essentially has the following form. And so, now we know that this is an epsilon naught times a chi, an effective chi which can also depend on E squared multiplying E, right. So, then we go back to our earlier definition of the refractive index, where we essentially had n, the refractive index, to be the square root of 1 plus the susceptibility, right, chi 1. Now, we replace chi 1 with this effective susceptibility, chi effective. Okay. So, that is what is replaced in this expression, and as a consequence of this, now refractive index essentially becomes something equal to, that is n is equal to, earlier we had n 0, the 0th order refractive index which did not depend on intensity of fields. Okay. So, this 1 plus chi 1 is n squared, okay. And then we have here a simplification where we pull n out of the square root sign and we have 1 plus chi 3 absolute value square of E divided by n naught square. Now, consider these terms, assume that the nonlinear term is much less than n 0 square in this case, then we can Taylor expand this term under the square root. In doing so, we have n within Taylor expansion, ignoring higher order terms in chi 3. Okay. We essentially have n to be equal to n naught plus 1, n naught times 1 plus this term which has a chi 3 absolute value square of E and n naught, but absolute value square of E is just intensity. Therefore, this now gives us a neat expression for the refractive index of the medium, which can now be represented as n is equal to n naught plus chi 3 absolute value square of E divided by twice n naught. If we set n 2 to be chi 3 by twice n naught, we get this famous relation, that is, one can say n as a function of intensity is n naught plus n 2 I. In principle, nothing prevents us from carrying forth such arguments to have an n 4 I square and higher order terms, but for now we will not consider these higher order terms. We will just take the leading order in I, and we have the expression n is equal to n naught plus n 2 I, where I is proportional of course to the absolute value square of the field. So, now you see that the refractive index is no more linear or essentially independent of field strength. Refractive index becomes dependent on intensity, and this effect happens in isotropic media too. So, therefore, this happens universally across various media. Of course, the values of n 2 can change from one medium to another. Okay, the values of n 2 can indeed change from one medium to another. Therefore, these are in some sense a more prominent effect than the second order effects. Okay. So, let us examine the consequence of the intensity dependent refractive index in the time frequency domain. Now, if we have a pulse propagating through a medium with a refractive index n, here we consider only the real part of the refractive index, then we realized earlier that after propagating through a distance z, the phase, okay, the refractive part, the phase is delayed, the phase delayed electric field essentially has the form E of z t at, that is at a point z after a duration t of propagation. The initial input field E0 of t multiplied by this factor exponent of I k n times z. Okay. Remember now that n is general, it is not just the linear refractive index, that is n naught, it is n naught plus n 2 I. For a pulse, I of t can be sketched as something in the time domain. We did this earlier, so we associated I with the pulse envelope. For example, right, so we identified I with the pulse envelope. So, the pulse develops an instantaneous time dependent phase phi of t, which is proportional to the intensity I of t, the way I depends on time. Therefore, I could be Gaussian, I could maybe be secant hyperbolic, you produce some other kind of pulse, whatever be it. The time dependent phase is imprinted on the pulse by mere propagation through this medium, right. So, now the phase that it develops phi of t can be written once again down, where we have Ez is equal to E naught t exponent of I k n 2 I as a function of t times z in this expression. Okay, what happened to the n naught term? N naught just remains, N naught is independent of intensity and whatever the case may be. So, it just becomes a constant additive to this, it is not dependent on time at all. So, for the purpose of this discussion, we will just ignore this term to keep the equations and the math simple. So, therefore, this is the beam, right. Look at the phase term phi of t is essentially now proportional to the temporal profile of the pulse n2 of I of t, right. So, the farther the pulse travels, the more the phase distortion it accumulates by traveling a certain length. So, if you put it in a fiber and propagate the pulse for kilometers, the phase distortion is going to accumulate many fold as against maybe propagation within the limited confines of a laboratory over few meters, alright. But what we are interested in is the variation of this phase phi of t with respect to time, and that can now be captured, that is the time varying part of phi is essentially equal to now kn2 times I of t times z. Now, we can see where we are going, right. Now, phi is a time dependent phase, as we did earlier in the arguments leading us up to instantaneous frequency. Remember, we had nu instantaneous is equal to nu naught plus d phi by dt. Recall that we had done something like this earlier. So, now we have a time dependent phase delay being introduced by the nonlinearity in the medium. As a consequence, we can now have basically new frequencies being generated, which we can see as to how it happens. We take the derivative of phi with respect to time, we take the derivative of phi with respect to time, and there we have, as a consequence of taking this derivative, new frequencies being generated. So, if the initial spectral content of the pulse was a single Gaussian lobe, after passing through the medium, self phase modulation leads to new frequencies being generated and the frequency spectrum having a fringe like structure. So, this is the consequence of self phase modulation. Why the fringes come about? We discussed this in an earlier lecture too. I can illustrate that through a simple graphic argument. If we have a pulse in the time domain, which has a Gaussian intensity amplitude, not only is this quantity I of t, this is also phi of t, this is how phi of t would vary in time. Now, what about d phi by dt? Let us plot the derivative of the Gaussian, right. So, the derivative of the Gaussian would essentially I am sorry, should have not done it like that. So, what is the axis on which I plot d phi by dt? This is the, I would call this a delta omega or a delta nu axis. Why I call it delta is because the pulse has an initial central frequency. Okay. So, depends on how we plot. We discussed this extensively in this course about using a central frequency nu, about a pulse having a central frequency nu naught. Okay. As I said, nu as a function of time, this is nu naught plus d phi by dt. We are just plotting the d phi by dt here. Now, for a given value of delta nu, we have two sources in time from which this frequency can be produced. So, we have two sources, S1 and S2. Two sources oscillating at the same frequency with emanating waves oscillating at the same frequency. What happened then in the space momentum case, space momentum domain, that is x k domain, we had fringes in the Young's experiment. Now, in this case, x is replaced with t and k is replaced with nu or omega. So, therefore, analogously we should see spectral domain fringes. So, these are the bright fringes and these of course are the dark ones, the nodes in the spectrum if you wish, right. So, that is the consequence of the intensity dependent refractive index in the time frequency domain. It leads to the effect of this spectral modification due to self phase modulation. Self phase modulation, the name is very self explanatory. A beam passing through a medium of appreciable third order nonlinear coefficient or appreciable intensity dependent refractive index coefficient N2 will modify its own phase. So, it is a kind of self action but not linear, it is in the non-linear sense. In the non-linear world, self action is everywhere, it is not a rarity, unlike in the linear world where we can ask questions about it. Now, that is for today. We want to examine the temporal effects of chi3 in this discussion as we did. So, we will take a brief pause here. If you have any questions, you can we can talk about it.
So we are getting frequency and current
Pardon?
this interference.
The interference, yes.
So we are getting in current part. So how this interference happens?
So Ritesh, what happens is the following. We can view it in this way. So we had an intensity envelope in time. This is I of t. This could also be phi of t. And you had, as a consequence of this, you basically had here we would have a zero crossing. So you basically have, as a consequence of this, we can call this the delta nu axis, so that nu total effective is nu naught plus delta nu, which depends on t. Nu naught is kind of constant. So you have now two sources which are at times t1, t2. These produce frequencies nu1 is equal to nu2. Both the frequencies are equal because the values of delta t corresponding to these, say delta nu1 or delta nu2 are the same. You agree? Look at this sketch. This is the derivative of the Gaussian. So this will give us, as a consequence, the same frequencies but at from two time points within the pulse. So as a consequence, what happens is that you can view this. Suppose I have a spectrometer, the pulse is proper. This is the t axis, this is also the z axis. Suppose I had a detector measuring the spectrum of this pulse. Now this source, this detector sees two sources, two coherent sources supplying waves of the same a wave of the same frequency. So therefore, one source produced this wave, okay. the next source could have, it starts say here, right. So, it could have produced the wave with the same frequency, but with a phase difference like this or something in between. Yeah. These two are oscillating at the same frequency. The detector simply measures the sum of these two signals of the same strength. So, here at this frequency, as a consequence, when we, if I now plot on the frequency axis, we have the central frequency omega naught or nu naught. Let us say all other frequencies which deviate from this, they can either go through a constructive interference or a sorry or a destructive interference, depending upon the spacing between the two. There could be another pair of frequencies which are generated, say here, another pair. So, here the frequencies, these are all, this upward lobe contributes to frequencies which are on the positive side of delta of nu naught, and the negative lobe contributes to these frequencies. So, that is essentially the consequence of cell phase modulation. So, it is these slits which the process places at different instants in time, different locations apart in time, which lead to this. Okay. So, that is a sort of the consequence of cell phase modulation, which is, you can say, interference in the time domain fringes in the frequency domain, right. So, elsewhere we had interference in the spatial domain and fringes in the k or theta domain, right. So, the angular domain or the reciprocal of space, which is the spatial frequency domain, right. So, that is cell phase modulation.